Okay, so I'll continue with the. I think yesterday mean like Monday we wrote down the equation for drain current. That's for the non-saturation region and the non-saturation region and the saturation region, and this is for the NMOS. Same way we do write. We can write down for the PMOS. So in case of the PMOS, and please note that we are only discussing about the enhancement mode, right? We are talking only to the enhancement mode one. So for case of the PMOS, the drain current in non-saturation region ID, we can write down Kp and twice VSD plus this VTP VSD minus VSD square, right? So we just use the different nomenclature. So just to distinguish for NMOS and PMOS. So there's a drain current, and for case of the saturation region, ID is simply your Kp and twice of VSG plus VTP. Not twice, the Kp, VSG plus VTP square. So this case Kp is conduction parameter, which is your if we remember it, W by 2L mu P and then COX, right? So this is the gate capacitance per unit area. Mu P is mobility for the holes, because holes are the charge carriers here in this channel region, and W is the width length ratio, right? So this is what we write down. So it means for the P channel MOSFET, if it is to bias into the saturation region, then for the VSD has to be larger than the VSD saturation. That's your, and this VSD saturation voltage. In the same way we wrote for NMOS, so we can write down for SG plus VTP. This threshold voltage, actually VTP is your negative in case of PMOS. So this eventually this is VSG minus becomes VTP. So case of, if we just see that for NMOS, case of NMOS, so we have the same equation. So VTN is a positive, greater than 0, whereas in case of the PMOS, the VTP is less than 0, right? So now I come to this equation. Okay. Oh, sorry, not for this family of curves. I think we discussed before also. So just to recall it, so we are going to work out. We like to work out onto this load line, right? So these are the set of different curves, right? When let's say we put up a gate to source voltage, let's say 2 volt or 3 volt, which is much larger than the VTN. So channel is formed, and there is when we apply a small signal, the current flows through the device, and then we get a characteristics like this. So other than since it's an ideal one, but actually there is some finite slope exists. There is a finite slope that exists into the onto this output characteristic. So what do I mean? Like in BJT, we have seen that there is a finite slope that so it means something like this. So eventually this is not flat, but something like this characteristics. So which has certain amount of finite slope. This finite slope comes because of channel length modulation, right? So if we recall it, channel length modulation means here. So of course the channel become tapered, but as we keep on increasing, let's say the voltage here, so the channel length is get modulated, right? So region is actually gets smaller. So this modulation actually give rise to the finite finite slope into the output characteristics. So that's the drain versus the VDS. Right, so this we can write down in the same way we did for the early voltage, in kind of like early voltage in case of the BJT. So in this case, if we extrapolate, let's say onto this side, if we extrapolate this curve, so it will meet on the x-axis somewhere negative. It will meet at the on the x-axis negative. So V, some voltage VA. So we can define it. So the slope here is nothing is 1 over R naught. So R naught will be 1 over the slope of, because we are finding ID versus the VDS, right? So when the MOSFET is biased in the saturation region, so the drain current we know that's independent of, but output has a this finite slope. So the VDS it goes to, let's say, some voltage minus VA when it's, I'm talking about this VA is somewhere here at this point. So in this case, ID, the drain current, we can write down as an Kn VGS minus VTN square and 1 plus lambda VDS. So this is in saturation. So lambda is a positive quantity and it's called as a channel length. So this lambda is this positive quantity called as a channel length modulation parameter, is referred as a channel length modulation parameter, right? So which is nothing, so the voltage VA that comes to be a 1 over lambda. So R naught basically we do it, R naught would be your slope, since we are finding a slope on this one. So the change in the drain current and change in the onto the change in the VDS. So we find it out, so we can get the from this equation, with the help of this equation, one can obtain R naught, which comes to be your, so this R naught one can write down in terms of the V, that's the voltage VA, and divide by comes to be ID. Okay, so Q I'm writing in terms for the quiescent point. So let's say that I'm going to draw a line quiescent point. So there's a drain current at the quiescent point. So that's your finite output resistance for this slope of the for this NMOS. Okay, so I think this problem you might have done it. So probably okay. So if we draw a load line, let's say for example, so load line means simply what you're going to find it out. We can write down the load line for, let's say, if you draw a line on this. So what's happening? Right, so this the point, we get it. So the point at which it intersects, so whether it is here or whether it's here or here or here, right? So all these are the nothing, these are the point is, we call it the quiescent point. So what you see that as we increase the gate to source voltage, let's say this is situation for the NMOS. So as we change the VGS, as the VGS increases, Q point shifts up, right? Not increases, means shifts up. So the Q point shifts up. So it may happen that, so what I would like to mention from here. So we will write down, let's say we make a circuit and we write down now kind of like a load line for a given circuit. So the Q point can move from here to here. It may happen that if the VGS is let's say if the VGS is large, so what you can see that the point as the VGS as the gate to source voltage keep on increasing, it may happen that transistor, the device may enter into non-saturation region. So it means there exists in a transition point. So these transition points are basically are nothing. These are the transition point. So because what I'm talking about, let's say the VGS is increasing the VGS on this side. So since your VGS is increasing here, the VGS is increasing. So the Q point is moving right onto the as VGS, let's say different VGS values. Maybe let's say this 1 volt, 2 volt, 3 volt, 4 volt. But you see the Q point is moving, right? The Q point is shifts up. So it may happen that at certain point value, a certain value of the VGS, the transistor may enter into the non-saturation region. So one has to be a bit careful in the that the voltage, the gate to source voltage should not be large enough that the device is supposed to be work onto the saturation region but enter into the non-saturation region. So it may happen that for certain values of VGS, this may result into the non-saturation region. So these points, or let's say these points, we call as a transition parameter or the transition points. So basically, one can calculate based on using the load line and the equation which we have written for the drain current. One can obtain, or one can write down, well, let's say one can obtain with the help of equation, one can obtain these transition points. So the values of VGS below which it will be a saturation region, but after or greater the values of the VGS, it will be into the non-saturation region. So let's look into one example here. So okay, so let me, before that, I think I need to provide you one circuit. Okay, let's say VDD, RD, let's say R1, R2, and then some coupling capacitor, and this is, let's say, VI is here the input, right? Coupling capacitors, you see, and this is it means, so what are these are the gate, drain, and this point is your source, right? So it's a DC equivalent circuit would be your, so its DC equivalent circuit would be your simply this is R2, and so this voltage at VG at this point we can use the voltage divider. So that's a VG, which is nothing, the gate to source voltage. We can find it out by the voltage divider. This is R2 by R1 plus R2 into VDD. Now if you're, so I think if the VGS is greater than VTN, that's the threshold voltage. right? So that's transistor is, we consider the transistor is biased in saturation. So whenever we solve let's say the problem, let's say we always assume that the transistor is biased into the saturation region. It may happen then for parameters, it may not be, if you get it by the, let's say, circuit analysis part. If this doesn't happen, that means the assumption is wrong. But we assume, we start with the assumption that the transistor is biased into the saturation. So if the gate to source voltage is larger than VTN, so it means that's because and assuming that it is in a and assume that the transistor is biased in saturation region. Right, once the transistor is biased in saturation region, means the drain current would be given simply by Kn VGS minus VTN square, and the drain to source voltage, so that's your here the VDS, that's your source, this is a drain, this is a gate, that's a V. So VDS would be simply given by the VDD and minus ID into RD. Right, so that's uh, the way you will attempt the let's say we target the solve the problem, or let's say we understand this kind of like a circuit on the MOSFET. So it means if your, we know that VDS, if it is a larger than the VDS saturation, so what does it mean? That is in saturation region. If your VDS is less than the VDS saturation, so that's reason means non-saturation, and this means the saturation. So what is the VDS saturation voltage is your VGS minus VTN, right? So one has to obtain the, let's say if your the VDS, which let's say we obtain from the analysis, if it comes to be larger than the VDS saturation, so we are simply say that it is a, the device, the transistor is into the saturation. So this point is your VDS saturation. So for the values here, so this is in saturation, and here it is non-saturation, right? So and we can also estimate, one can also estimate the power dissipated in the device means the transistor. So that's would be your, the power that's dissipated into the transistor would be your the current which is flowing, ID, and the drain to source voltage VD as here. All right, so now as I was saying to you for the previous one, how we are going to find out these transition parameters. Let's say let's look into the this example where let's say the VDD is known. For example, let's say obtain or say determine the transition parameters of a common source circuit, which is, let's say, and assume VTN is 1 volt, Kn is 0.1 milliampere per volt square. So the VDD is your 5 volt and RD is your 20 kilo ohm, right? So it means I'm talking on to this circuit. VDD, RD, R1, R2. So only let's find out the transition parameter. So transition parameter, I was saying to you, that means one has to find out for which values of the, let's say, the voltages, right? This transistor would be in saturation region, or this transistor would be into the non-saturation region. So kind of like those parameters. So what does it mean? So at the at this at this as I said that, so at the transition point, so how are we going to find it out? So at the transition point, so let's say we don't know what are, so let's say this is ID, VDS, and we have here, so basically this is the transition point here, right? So this is basically a transition point. So here it is a non-saturation, and here it is a saturation. So at the transition point, your the VDS at this point is, VDS is saturation. So VDS is nothing, is a VDS saturation, and the VDS saturation for NMOS is simply given as an VGS minus VTN. And from the load line, what we, if we write down from the load line analysis, VDS is your VDD minus ID into RD. So that means, so at the transition point, this VDS is equals to the VDS saturation, so which is nothing, is a VGS minus VTN. So we can write down as an a VGS minus VTN is equals to VDD minus ID and RD, right? So now let's assume that the transistor is in saturation region. Assume that condition, because the equation, your drain current equation, we can use it, Kn VGS minus VTN square. So we make use of this. So this we can write down as an VDD minus Kn VGS minus VTN square into RD, right? So what you see from here, what from this equation now, what is unknown? What is the known parameter here? Sorry, what's the known parameter? What's the known parameter? What's the unknown parameter here? Anyone? So the VTN is given to you.
VGS.
VGS. Yeah, VTN is threshold voltage is given. The Kn parameter is given, and VDD is given, and RD is given here. So the unknown is VGS. So that's would give the value of the VGS, right? So maybe you can just quickly calculate it. If you have a calculator, you may quickly calculate. So the VTN is 1 volt, 0.1 milliampere per volt square, and then RD is your 20 kilo ohm. So can we quickly estimate the value of the VGS? Like you will get certain number, of course you will get some number. So if your gate to source voltage, if it is a less than this, so it means we are in saturation region. If you are having a if the gate to source voltage somewhere here, if it is larger than the this value, it means this means the device is going to enter into this non-saturation region, right? Because you're the key point, because the key point moves up as we go for the higher value of the gate to source voltage, right? So means the Q point, let's say initially it was in saturation region, but somehow we increase this gate to source voltage, it moves up and then it reaches to this point. And if it's slightly up, it's going to onto the non-saturation region. So one has to be very careful while designing. So most of the application based on this transistor, the device has to be biased in saturation region. So that's the most, or let's say basically the amplification purpose, or it has to be biased into the saturation region. So that's the reason that we have the now voltage divider. Again, there is a voltage divider circuit because the gate voltage at this point can be controlled with the combination of an R1 and R2. Right, so I think you can estimate this value. You can find out this value. And then you can estimate the, once we know the VGS value, what's then you can find out the current, that's drain current, because the VGS is unknown. So once you calculate the VGS from this equation, you plug in into the, for drain current, you can obtain the this ID value here. Right, so you can find it out. So
Sir, VGS will be positive only.
yes, it will be positive because this has to be positive for NMOS, common source NMOS. Yes, you will get the quadratic equation form. So So one more thing, I think I know what's the value you get it. If the VGS is less than VTN, in that case, you are simply in the cutoff region, right? So if your the VGS is less than VTN, so it means we are somewhere onto this line. So no channel is formed. So it means once no channel is formed, so there is no current will be flowing through the device. So it means the device or the transistor is in the cutoff mode. So if the VGS is less than VTN, so somewhere something like here. So that's basically the cutoff. So you can calculate and just let me know if you are done. So we are using both PMOS and MOS. One can create an CMOS, that's your complementary uh, metal oxide semiconductor. That's basically whenever you look into any chip, current any chip, whether it's in a mobile, whether it's in your mobile phone, whether it's your in laptop, anywhere, all electronic, right? So it's basically is based on the CMOS. So basically CMOS means we are utilizing both the NMOS as well as in a PMOS. So that's we call as in a CMOS, which is nothing as in a complementary MOS. So metal oxide semiconductor, right? So one can do into the both ways. One can have a P-type substrate, or we can have a N-type substrate. So in case of less, I'll make a one drawing here. So considering how does it look like. So this is a P-type. This is a P-type substrate, the body, and plus and plus and P plus P plus here, and just hold on the top of this is here. This should be okay. This not become little bit congested. So basically, okay, and this was sketch. This is cartoon sketch. So the dimensions are not proportionate. So these are, I think, just to show you. And so this is your oxide layer, and the top of this is a metal here. Okay, and in between there's a polycrystalline some stuff. Metal. So this is your drain, gate, source, and on this side is again some kind of polycrystalline or kind of like a dielectric. And on this again you have the drain, gate, and source. So basically and because for to make a PMOS we have to have a N type. So this one creates here the kind of like an N well, and then you have P plus, so drain and source. And in this case you have channel is being formed on here, right? So this to this here is in a NMOS, and this is in a PMOS. So this is kind of like both functionalities are embedded. So that's because in a complementary, because they're complementary into their nature. So this kind of like a transistor basically used basis for creating all your processor and CMOS techno, that we say that all the functionalities are achieved based on whether it's your and all kind of like digital or analog, or whether it want to computation. So everything is basically driven by the CMOS technology. it makes use of both NMOS and PMOS. So other than this, okay, so we'll be doing onto some numerical examples only. So basically let's do it for okay, so let's say you find out the source to drain voltage required to bias a P channel enhancement mode MOSFET in saturation region. Consider, let's say we assume the parameter basically talking about enhancement mode PMOS, and parameters are given here. Kp is your 0.2 milliampere per volt square, VTP is minus 0.5 volt, and ID is 0.5 milliampere. So one has to obtain the VDS, drain to source voltage, source to, sorry, not VSD. VSD, that's the source to drain voltage required to bias this PMOS in saturation region. So what's the voltage is source to drain voltage required to bias, let's say, PMOS in saturation region. Right, so this we can find it out. So because it says saturation region already, so the ID is your Kp VSD plus VTP square. Right, so that would give us the, I think, VSD, not VSD, sorry. The equation is now ID is Kp VSD plus VTP square. So ID is known here, Kp is known, VTP is known. So this will give us the value of VSD, right? And so what we have to do, we have to find out the source to drain voltage. So that means, so that it is in a saturation region, right? So it means we have to find out VSD saturation, which will be your VSG plus VTP. So that would give us the VSD saturation voltage, because it says that the source to drain voltage required to bias the PMOS in saturation region. Right, so I think this we can obtain. So I think very quickly you can find it out. VSD from here, Kp is 0.2 milliampere. So make sure the units wise, right? And what we have, this is VSD and minus 0.5. Right, so the you will get the from here, and the current is given 0.5 milliampere, so it's fine. So this is 0.5, 0.2 milliampere per volt square. So this is everything comes in terms of the volt minus 0.5 square. So from here you can find it out the value of VSG. Once you calculate the VSG, one can obtain the source to drain voltage. Okay, so let's one more examples we did for the common source NMOS. I think this was common source, let's say NMOS, common source PMOS. Okay, I'm just drawing the DC circuit. We are only restricting ourselves till the DC analysis part here for the MOSFET. So just we are going for the DC circuit here. VDD, RD, R1, R2. Right, so this is your gate terminal, this is your drain, and this is the source terminal. Right. Maybe that close here, and basically this is nothing the plus minus VGS, and what we are obtaining is plus minus VDS from here. For this one, R2, R1, VDD, RD, VSD, and then we have VSG here. Right, so in this case VG or VGS, VS, so VG would be your R2 over R1 plus R2 multiplied by VDD, and VSG, the gate to source voltage, would be your VDD minus VG here. Right, so assumptions, as I mentioned, that we assume that the value here, the gate to source voltage, it should be, since threshold voltage VTP in case of PMOS is a negative, so if we take in absolute or the magnitude only, take the positive magnitude, so it means the VSG has to be greater than the VTP, and assume that in both the situations, so assumptions are the same. So in both the situations, so we assume that transistor is biased in saturation region. So we assume that transistor is biased in saturation region, right? So that means we can use equation ID Kp VSG plus VTP squared here, and in this case ID is Kn VGS minus VTN square. So these both are equations. These are the saturation region, right? This is the current in saturation region. This is the current in saturation region. And what are other condition I think I mentioned to you? So VGS is greater than VTN. We are always assuming that the channel is, the transistor is on, so that the, and what else, we, for saturation region, the VDS has to be larger than the VDS saturation. So in the same way here, VSD has to be larger than the VSD saturation voltage. If VSD comes less than the VSD saturation, so that means this the transistor now in non-saturation region, that's in triode region. In the same way here, so if VDS is less than VDS saturation, so transistor is in the non-saturation region. So in that case, if it comes to be like this, in that case, if you want to find out the drain current in that situation, so in both the cases, so the equation is, now we write down, we find out the drain current with the help of the equation which is for the non-saturation region. That's your Kn twice Vgs minus Vtn Vds minus Vds square for case of the NMOS. For case of PMOS is a Kp twice of Vsg plus Vtp Vsd minus Vsd square. Right, so let's look into, I think we'll do examples. Okay, so let's assume for parameters R1 is equals to 30 kilo ohm, R2 is, let's say, 20 kilo ohm, and RD is 20 kilo ohm. So what you have to find out, VDD is 5 volt, Kn is here 0.1 milliampere per volt square, Vtn is equals to 1 volt. Right, so this is basically the circuit on this circuit, common source NMOS DC circuit. So you need to find it out. All the other parameter means the drain current, and check whether the transistor is biased in saturation region or it's in non-saturation region. So we have to find out the gate to source voltage VGS. We have to find out the VDS. Then it will confirm and find out the VDS saturation, and then check whether the transistor is biased in saturation region or not. Right, so kindly do it. First step is to find out the VGS. Check whether it is larger than VTN. If it is larger than VTN, it means that transistor is on. And what you need to find it out, you need to calculate the for the VDS. So to calculate the VDS, you need to assume. So assumption would be simply that assume that the transistor is biased in saturation region. Right, if it is a bias in saturation region, right, so you just apply ID is equals to Kn VGS minus Vtn square, right, and find out using a load that equation. The output loop means from the drain to source, that of VDS is equals to VDD minus ID into RD, and this will give the VDS. Find it out VDS saturation, which is VGS minus VTN. Right, we know this number, and then you have obtained. We are going to find it out VDS from here, considering that is in saturation region. Right, so this VDS should be what we obtain from this equation. Let's see if I write down the 1 and 2. So the from 2, the VDS, whatever we get it, if it is larger than the VDS saturation, your assumption is correct, and then it means that's in saturation region. If it is not, then you have to use the non-saturation region drain current to find out the drain current of the device for the non-saturation region. So kindly do it. Let me know this values. So this is for NMOS. In the same way we can do for the PMOS. So in case of PMOS, the parameters we can write down for PMOS common source. Let's assume R1 equals to 50 kilo ohm, R2 is 50 kilo ohm, VDD is 5 volt, RD is 7.5 kilo ohm, VTP is minus 0.8 volt, KP is 0.2 milliampere per volt square. Right, so you have to do the same. You have to find out the VSD, you have to find out the VSD and check it out, the condition, whether it's in saturation or non-saturation region. Right, so please try this. How many you've done it? Sorry, the previous one. VGS. And one more point here, if we compare with the BZT and this FAT device here has a high input impedances. I think I mentioned in the beginning as well, because the transconductance parameter that we obtain, it's larger, so it has a high input impedance. So that's when we use, let's say when we go for the op-amp, right? You've done the experiment on the op-amp, operation amplifier, so right, and I think you may have come across about the virtual ground concept while doing the experiment, right? So, and this is because the first block, that's when we open the operation amplifier, let's say IC741 chip, which we are using in virtual mode right now. But in, let's say if I open it and see there is a kind of like many kind of transistors are there. So the first block that comes to out to be is a differential amplifier, and that's all are based on, yes. And all are made for this MOSFET. So this is not a not a BZT, but it is when you look into IC741. So there's around 16 to 40 transistors are there. All those transistors are nothing. These are FET MOSFETs. All right. So basically, it has a high input impedance. So probably I think that we'll introduce you in the next week. So next week we plan to start the operation amplifier, and please do it these problems. It done? Anybody got it? The answers? Yes. Yeah. Anyone got those values? VGS
Sir, 2 volt.
is 2 volt. Okay, and then you have to find out the drain current. Once you obtain the drain current, you substitute in this equation, you find out the drain to source, the voltage. I think it's an output voltage, so that would give VDD minus ID into RD depending on the value of ID, and then we obtain the saturation voltage VDS. Right, so in the same way, you can obtain for common source circuit for the PMOS and check it out whether for this set of parameters, whether the device is or the transistor device means transistor is biased in saturation or non-saturation region. So that you need to confirm, like it for both the problems, one has to make a check actually. If you any see any other questions? Yeah, one more thing. I think tomorrow one, as they feel, I think there's no navigation is like backward navigation is not being provided. Right, so I think soon we'll may receive an email. So tomorrow class test, there's no kind of like only forward navigation is there.
Sir, duration also.